Hi everyone, my name is Neha and this is the 11th lecture on Introduction to Automation. In this lecture, we are going to learn about flow sensors. Flow sensors, they measure the quantity of fluid material passing by a point in a certain time. The material which passes, it can be liquid or gas. Now, let's see pressure-based flow sensors. So this type of flow sensor, it is based on the fact that pressure in a moving fluid is proportional to the flow. In this type, the two ports are used, P1 and P2, from which the pressure is measured, and the difference between these two ports of the pressure, these two ports is taken, and that pressure difference will be proportional to the flow of the liquid. Now, on the right hand side, you see the similar picture of a pressure-based flow sensor. And here, orifice plate is used, which is commonly used in the flow sensor, and rest of the things are same. From here, the fluid will enter or the gas will enter, and from here, the gas or the fluid will go out. And these are the two pressure sensors, and the difference between these two sensors will be taken up, and that will be proportional to the flow, and that flow could be of gas or liquid. And here you see this defines the area of the hole and the area of the cross sectional. So the big one you see here, this is the area of the pipe or the pipe cross section, and the inside circle you see this designates the area of the hole. Now this pressure-based flow sensor, as I told you, that it is proportional to the pressure difference between the two ports, and it can be calculated by using this formula. So this Q here stands for the flow, and C is the coefficient of discharge, and typically its value is 0.63 for water if the orifice hole is at least half the pipe size. Next we have this A, and this A stands for area of the orifice hole, and then we have under root of 2G by D, where D is the weight density of the fluid, and then G is for the gravity, and its value is 384 inches per second square. And then we have the pressure between two ports, which is calculated in PSI. Now the application of this pressure-based flow sensor, it includes in power generation, it can be used in gas generation, in water treatment plants they can be used. So there are a variety of applications where the pressure-based flow sensors can be utilized. Now next we have Venturi flow sensors. A venturi is a gradual restriction in the pipe that causes the fluid velocity to increase in the restricted area. The area of higher velocity, it has lower pressure, and here the difference in the pressure between these two ports you see, P1 and P2, that will be directly proportional to the flow of the liquid in the pipe. So this type of Venturi flow sensor, it tends to keep the flow more smooth, but both the previous which you saw, orifice and this Venturi, they both causes pressure drop in the pipe, which may be sometimes objectionable. Now if we see the application of Venturi flow sensors, then they can be used in pipelines at wastewater collection system and treatment plants. They can also be used in crude oil pipelines, airflow in the car engines, etc. Now next let's see a pitot tube. A pitot tube is one of the simplest flow sensors. It is used in a wide range of flow measurements. Applications such as airspeed in racing cars and Air Force fighter jets. So this is one of the applications which you see here, and all these are the pitot tubes. So in this one, pitot tubes, they cause minimum restriction in the pitot tube. And the pitot tube, it is basically a small open tube that faces into the flow. Now, one of the tube, it faces into the flow and it reports the impact pressure, while the other tube which you see here, faces, it basically opens perpendicularly to the flow, and it reports the static pressure. So here this impact pressure through which we are getting through this tube is always going to be greater than this static pressure, and the difference between these two pressures is taken, and that difference is proportional to the velocity and hence the flow of liquid into the tube. Now next, let's see, we have turbine flow sensors. So this turbine or spin type flow sensors, they employ a paddle, wheel or a propeller placed in the line of flow. The rotational velocity of the wheel is directly proportional to the flow velocity. So you see here in this picture, this is the propeller, and this propeller will rotate based upon the pressure of the liquid going into the tube. So this rotational velocity of the wheel, it will be directly proportional to the flow velocity. And here you see a magnet is attached to one of the blades. You can see here it is shown with this blue color, and this magnet will basically respond to this Hall effect sensor which is mounted on the pipe. So Hall effect sensor, it gives a pulse for each revolution of the plate. So as this paddle revolves, so every time it reaches to this point, then this Hall effect sensor, it will detect one pulse, and so on. Here on the right hand side you see the picture of a turbine flow sensor, and that's how it looks like. And it can be used on multiple applications. Some of them has been mentioned over here. It can be used in oil and gas industries for water injection, test and production separators. In natural gas pipelines it can be used. It can be used in aerospace, in defense, for engine testing. It can be used for fuel flow measurement, for monitoring fuel supply to ship engines. It can be used in power generation also for custody transfer, in industry and municipal for building automation, etc. Now next we have magnetic flow meters. It says if a liquid is even slightly conductive, a magnetic flow meter, it can be used. So magnetic flow meter, it has no moving part and it presents no obstruction to the flow. You can see here a magnet is placed here, and under the magnet we have a non-conducting section of pipe which is placed in this way, and then on the sides we have electrodes placed, and through these electrodes the output voltage is taken. So when the moving fluid is there in the pipe, then it is like the moving conductor in a generator, and it will produce a voltage, and that voltage is going to be proportional to the fluid velocity, and that fluid velocity can be detected through these electrodes, and the output voltage can be obtained, which will be proportional to the flow velocity. Now here on the right hand side you see the magnetic flow meter, and this is how it looks like. And the application, if it see these type of flow meters, they are ideal for water waste applications or any kind of dirty liquid which is conductive. They produce accurate output voltage in that case, and they are not very good for if you want to use for distilled water or liquid which consists of hydrocarbons. Now let's see one problem based on flow meter. So the problem says an orifice plate flow sensor is used to measure the flow of water in a 6 inches inside diameter of the pipe is given here. The orifice plate has a 3 inches diameter hole. The pressure difference across the plate is 0.5 psi. Find the approximate water flow in the pipe. So for this problem you will be using this formula. So here we see that the value for this coefficient is going to be 0.63. We can start with this value because 3 inches is half of 6 inches, which is our inside diameter. So we will take this value into our equation, and then we have area which is equals to pi r square. So as we know in this picture, if you see here, the large circle which you see here, which says the area of pipe cross section. So this large circle, which is A2, it has a diameter of 6 inches. So this is the diameter, and then inside we have A1, which is the area of the hole, and this blue color represents the orifice plate. So this inside diameter is our 3 inches. So we will take the radius of this value, and then radius will be 1.5, and then we will calculate the area of the hole. So gravity constant we can calculate using this value which is given over here, and then the difference between two pressure is already given, which is 0.5 psi. So we will write this here, and then the weight density of water is this, and it will be this in lb per feet cube. So we'll put this value into the flow equation. So after putting into the equation, you will get this answer, which is 453.03 inch cube per second. So this will be the answer for this problem, and this is the end of the lecture. Thank you so much for watching.